cardiac system, I guess your heart would be the central unit process, and I think it's the same thing. I look at the filter as probably the central if you are doing iron manganese removal, because you're doing your surface prep before, you're going through your filter, that can affect how much is coming through. And turn it up. I guess I need a little louder. I'll try and speak up too, but yeah, we were messing with that this morning. Can you hear me in the back? Yeah? Okay. Perfect. Sounds good. So, I guess we're going to get to how to measure, looking at various tools on how to measure the effectiveness of your filter on removing particles, and also how effective you're backwashing it to maintain that health from what it was designed for. And I think also another thing to understand when you first, for me anyway, when you first design a filter, every water is different. Every one of your water systems is unique. It has a unique water quality. So a lot of times our designs are based just on, typical industry standards and kind of your average water. But you can think of your actual filter in place as an ongoing ideal pilot study where everything's exactly the way your water is going to be from season to season. Temperature changes, seasonal changes, how your distribution changes, how much water you're putting through the filters. And by looking at that from year to year, you can see, by understanding some of the concepts and design concepts of how you designed that filter originally, and then measuring how it's performing and how it's changing from its original condition and the job it's doing, if maybe you could do things by adding a little bit of one media size or another media size, or when you do go to renovate your filter, the things you can change. So I think that's a benefit, not just understanding your health, but looking at it, how could we tweak design if we had known what we know now? So we might as well use our filters and kind of have them tell us a story of what we could have done if we had known when we designed it initially. That. Remove my clipboard.
It's under the table there. Under the table there.
Okay, thanks.
Just slide it on.
So you can think of, you still hear me? Yep. You think of a filter conceptually as a particle absorber. So if you think of a sponge as a water absorber, basically you have voids within a sponge. You're sopping up water. You go into your bucket, bring it out. It's got capacity to absorb more water. You look at your filter the same way. It's got void space between your media particles. As you're think of a bunch of basketballs sitting together, you're going to have voids in there, and those voids are your capacity to hold particles. And then with your backwash, you're lifting those particles, those media, flushing out the particles between them, like bringing out your sponge, and then hopefully you have as much capacity as you initially did, and you can maintain that for years. The effectiveness is not quite that simple because there's other, the preparation, like the coagulant you use, the pre-treatment of your water, and how you're preparing those solids, what type of flock you're developing. The surface property of the medias themselves, there's medias you can charge like green sand, you can put a manganese oxide coating on it. The relative size of the media particles within each layer, like your anthracite and your sand, and the chemical characteristics of your water, which again are going to vary from utility to utility and maybe even from season to season. So some of the key things are attachment mechanisms for absorption, like your flax will often have a positive charge, ferric hydroxide, and your sand or your media will often have a negative charge. So there's an attraction there. Physical absorption, would be like a GAC, but also you have a certain amount of physical absorption with a manganese oxide coating on your green sand. Like precipitates want to be next to a like material, so it tends to attract the manganese oxide coating. So really, straining is how we often just initially, if you mention a filter to somebody, everyone thinks straining, but you really ideally don't want to design a filter just based on straining, because if you think of it, it's just you're trying to strain through like a sieve. The tendency is, if you just designed it for like a specific size and didn't consider all these other factors, it'd be like potential for wrapping a sponge with saran wrap. It loses its capacity because all the particles would blind off the filter at the top. So relative size, you want to have, to avoid straining, the prolonged filter ones, you want large to small. So ideally you want your large, like your basketballs on the top, volleyballs, softballs. So that as your larger particles, your smaller particles can sift down, farther down into your bed, farther down into your sponge. They won't be acting as that saran wrap, so you can utilize and fill as many voids in that filter as possible. And parameters have been identified to help in the selection of media sizes and densities. We'll talk a little bit more about densities later. But in general, if you just had a stockpile of media, the range of particle sizes in that are going to be greater than what. Oops. Just get a little bit into the design of how we design the filter, mainly so that when we look in the future we can see how we could adjust that. But when we're designing a filter, we look at things like D10, that's a grain size which 10% of the media is smaller than. So in other words, 90% of the media would stay on top of that sieve. D60 is grain size which 60% is smaller. And then the relative size, or the difference in size throughout your anthracite, let's say, is called a uniformity coefficient, and that's a D60 over D10, so that's a ratio. And so if you had exactly, your media was exact spheres manufactured, and they're all exact same size, you have a uniformity coefficient of 1. So the smaller that uniformity coefficient, the more consistent your media size is. Typical filter designs. Probably, that's why we have anthracite over sand for an iron and manganese filter, because your iron flocks tend to be bigger, your manganese tend to be smaller. So you really, since there's enough size difference, you actually get two different layers. So here's a typical size. Your D10 for your anthracite is about 1 on average, and it's about half that for sand. And the sand stays on the bottom of your backwash because it's heavier. It's about 2.6 versus the anthracite's lighter at about 1.6. And uniformity coefficients are about the same. It's either well over 1. I guess the only is if you had, I don't know that too many people have deep bed sand filters, but that if someone was going to intentionally design the filter for biological removal, that might be a good option there, to use anthracite and larger, because you're relying more on the attached growth on your media versus the actual particle and void sizes to capture your solids. In terms of backwashing principles, the objectives, of course, again, we're bringing out our sponge, we're flushing the particles and trapped within the voids in our media bed. We're scrubbing off any coatings so we get back to original cleanness of the media surfaces, and re-stratifying the filter bed so you get back with your anthracite on top and your sand on the bottom, or green sand on the bottom. So the design issues are to ensure that with your under drain and distribution of your water in the under drain and up through the bed that you have good fluidization. It's all fluidizing and lifting up so those particles can be flushed out of the voids. And want to provide good surface agitation, especially if you tend to have a water that's going to lead to a coating, whether it's typically it'd be like a biological type coating, but if you had a softening plant, it could be a calcium carbonate or other type coating. And then just ensure uniform distribution, so you're not getting a bunch of excellent, 15 gallons per square foot in one corner, 3 gallons per square foot in the middle. So here's some of the typical rates. You see, again, because our I don't know if you can call it, but the specific gravity of your, is why these are different when you have green sand. The specific gravity of your sand is about 2.65, and the specific gravity of green sand is about 2.4, so it's a little lighter, so you don't need to go as fast to get that fluffing, because the velocity and the density of water doesn't need to lift as much. That's probably the main point that I make there. And so just to look at it conceptually, what we've talked about beforehand, just in terms of how you can visualize this. If these are all, this would be the ideal placement of large particles or small. If this was our one bed of sand, our D10 would be, 10% of the media smaller than that. Our D60 would be 60% of the media smaller than that. And their uniformity coefficient would be that D60 over D10. And that kind of gives you your range of your particle size. So I think that's a good way to visualize it. If you were going to put the media in the order you wanted it and just stack it up, it's an easy way to remember. That's your D10, D60, so D60 over D10, that's your uniformity coefficient. Problem, of course, is that when you backwash, if you had particles the same density, let's just say the density of you had a bowling ball type density, you have bowling ball sized particles, and the same things for bocce balls. When you backwash, this water is going to lift the smaller particles up to the top, exactly opposite of what we want. And that's another reason why you don't want too much. Your uniformity coefficient usually kind of works against you, because when you backwash, it's going to go here. So that's why you typically see it specified uniformity coefficient less than such and such. Again, 1 would be perfect. And also another reason why you can't just have a deeper bed. If you really have 2 different sized particles, or maybe if you found you had 3 different sized particles, you might want more different sizes of media. So you get your iron. If this was our anthracite, we'd still be able to capture our iron here, and all of our manganese would go down through to the bed below. So to look at that, and this helps too to think if we do ever need to replace some of our media, that same principle though can work for us. If we just were to stack, for some reason we just were putting our design and we just wanted to take the time, we could put our anthracite on the bottom, large media to small media the way we want it, and our sand on top, large media to small media. But when we backwash, the lighter will move to the top, so our anthracite will come to the top here, and also the small will move to the top, and then everything would go in place. So that does show that if you are, let's say you needed some more sand in your bed you found, for some reason you decided, if you did your filter evaluation, you'd like more sand for more depth of manganese removal, and you didn't worry about the fact that you've lost some inches of anthracite, that's a possibility. You can just throw the sand in on top, and it will migrate to the appropriate place. And the same thing's true with anthracite. One of the tools when I was at University of Kansas with a national firm is this Expofill, and you can use that for any type of media. There's a pyrolusite, there's other medias that have specific gravities that are way higher. Anthracite's typically the lowest, but that could have different purposes if you wanted to have different objectives for your water. But you can use this tool to determine how much expansion you're going to get based on the specific capacity and the size. And it's kind of funny because I came back to Minnesota, and when I came to Bolten Menk, I called Herman, the guy who works with us, and asked him, hey, do we have this Expofill? It's written in BASIC, and I'm just, I can't get to it anymore. I'd like to have a copy of this program. And he said something to me. I couldn't understand him because I wasn't used to his thick German accent at the time. And then finally I hung up and I found a copy of the paper, and I looked and I go, hey, H. Raja, I wonder if that could be Herman. And I called him back. He said, yes, Steve, that's what I was trying to tell you. I wrote that. I can help you all. So he's the expert who wrote this program that we use down there at the national firm and in my master's program. Sounds kind of interesting. Another thing to think of again is that the reason it's not just as simple as a particle strainer is that, like for example, the city of Minneapolis, with their filters, they're able to remove viruses and bacteria, very small particles, much smaller than you'd think sieving would allow you to. And that is because of influence of chemical optimization. If you have poor chemical optimization, your turbidity will continue to stay real high and you get a lot of breakthrough through your filter, but the closer you get to optimum, once that filter ripens, it's going to drop way down until it's time to backwash and it'll start coming up again. And so they'll monitor, like look for a 0.1 NTU coming out of the filter, and you can do things like filter to waste if you do have that as a criteria. Most our groundwaters don't have that, but it's still important to understand that you can get a lot surface, chemical optimization or biological optimization if you're harnessing biological activity is really critical to the performance of your filter. But understanding what mechanisms are doing and how they could impact the long-term health of your filter is also important. So just want to touch on, real briefly, this is a whole presentation in itself, but that there are basically, I'd say, these three categories of removal mechanisms. Chemical, which is your typical, you have your weaker, less expensive oxidants to your stronger, taking your reduced iron in the aquifer and oxidizing it so it becomes a flock that can be removed in your voids. And typically that would be done with air and some detention, or chlorine is almost instantaneous, and manganese is typically done with permanganate. It's much more expensive, so you want to make sure you're kind of hitting these in order with least expensive to more expensive chemicals. And also, potassium permanganate, which you use here, has about 0.17 milligrams of manganese per milligram per liter of permanganate. So you're kind of working against yourself. So there's no sense in putting more potassium permanganate in your filter than you need to. You're kind of just causing your filter to get clogged up earlier and spending extra money. Physical mechanisms, we've basically been focusing on that, filtration and absorption. And biological mechanisms is harnessing lots of waters, especially south of the metro and west of the metro, have naturally occurring iron and manganese oxidizing bacteria in the wells. And actually, sometimes when I do these filter evaluations or look at these filters, actually find that even with the chlorine residual through the filter, these bugs are so wanting to be there, and they have kind of this party, this food coming by them and oxygen, that they'll be able to hide for a little bit from the chlorine residual if they form a slime. And then you'll just wonder why every once in a while our filter's going good, and then every once in a while we just get this sloughing out in the system. And the reason is because you're kind of fighting against the microbes that want to be there, and then you're not in control of when they slough off to a certain degree. And this is kind of how they work. They've got this filamentaceous nature. These are two different types of iron bacteria that we see in a biological removal. And they kind of reach their polymer, naturally occurring polysaccharide polymer arms out, can grab onto a piece of media, and then they form little chains. They have their food party as it comes by, and they're very slippery. So I've seen filters almost plug to the point where I'd say 4/5 of the filter's plug, because you can filter up to 5 times as fast through a biologically active filter. And everything's fine until you get to that point. All of a sudden they start seeing the head go up. So you can push a lot more water through that filter and get excellent removal. But you have to be real careful. If you're not carrying the chlorine residual through your filter, you just decide to shut off your chlorine or permanganate, think everything looks great. You got to make sure you understand the other implications, which is eventually you could plug up that bed. And especially if you have a weir type backwash, so if you're using just 3-foot head over your backwash trough, your typical center column filter, because as that gets more and more plugged, more of the water just takes the easy route and spills over the weir, because you're not forcing it with a direct connect backwash. So you won't even know that, oh, we're only getting 3 gallons of it per square foot now instead of 12. And this is kind of the last thing, is that these are some good curves that kind of keep track when you're doing a filter evaluation. Again, this is the turbidity curve we looked at before, that you might have a ripening period as when you first start filtering, that the meat is going to kind of, the fluffing that you had is going to kind of press back down. It's going to get back to business. It takes it a while for it to do that. Then you have your maturity time through the time of backwash is good. And the same thing, you might have a head. If you have a head limitation in your filter, so one of these might govern, but a lot of plants, it's probably good to try and find out what that is in a pilot, maybe just push your filters once and see what's going to be governing. If you have to really push your filters harder. But a lot of plants are just doing it, okay, we do it every other day, and that's fine too. So for filter evaluation now, we've designed our filter, we have it in place, we understand the concepts. Now we want to look at some of the tools that we can go and say, okay, I think it's a good idea to do one when you, like shortly after you start up, so you kind of have a baseline, what your filter health is when it was first designed. And then maybe every year you do it, and then maybe you switch to every couple years after you do a couple of these. But basically, good idea to do on a routine basis, because again, we can see information to optimize operation and monitor and maintain the health, see if things are changing. So again, we're establishing a baseline, starting point for ongoing optimization. We understand the process performance, which parts of our media bed are doing what. And then you just document and maintain good records. Because from year to year, you can say, okay, we did this change last year. We decided to backwash 10 minutes longer, or not 10 minutes, maybe a minute longer, or 2 minutes shorter, or at a slightly higher rate. And then you go back and do it next year. What was the impacts of that? Maybe we need to take another step forward. Maybe we can back it up. So appropriate maintenance steps for the next year. And then the ideal, of course, is to avoid surprises. No one likes surprises, So to make sure that if we see something's come or something needs to be adjusted, and even just to know what you're going to do when the next expansion or renovation comes along. So filter evaluation defined. I'm just going to read this verbatim here. It's a small, customized water treatment plant study with the potential for big returns, including capital savings, operational savings, and operational insight into improving and maintaining the health of your water plant's core unit processes. So the key is really that it's a customized study. I think talking to your operators, talking with your engineers, there's certain items in here where it's going to be clear, well, we don't need to be concerned about that. And there are others we are, but we'll go through them all. And how much we look at pre-treatment. Do you have issues in your distribution system that might be tied to your filter? Do you have occasional chlorine odors? Do you have occasional reductions of your pH in the summer? All those things can ultimately, I found, tied back to the filter. There's a lot of times you can address even things that the users tap that are seasonal things, pH or corrosion issues, you can address within your filters. Then it helps to increase insight. I like to, after I've done one of these, bring everyone together and say, okay, let's do kind of this presentation we're going to do now, but customized to your filter. What did we see? What do we think we can learn? What are some things we could do differently? And then things very often you see reduced chemical costs, reduced backwash runs. You might be backwashing longer than you need to. Be avoiding unnecessary costs, and then ultimately no surprises. So again, we're looking at the whole system from the well water all the way to the towers to the taps. Oxidation reduction potential, that's something I'll track, especially if we think you have water that likes to be biologically active. And another same thing with dissolved oxygen. Chlorine residual we want to look at regardless. And then if we start having things with like colloidal breakthrough, you can actually do iron manganese particulate size analysis where you actually use little filter papers and little cartridge filters and see if your flocks are colloidal or not colloidal, and then you can see, well, maybe better if we use air as an oxidant versus chlorine as an oxidant. And again, the three are chemical, physical, and biological removal mechanisms. So we can look at the chemical doses and feed points. Is there anything we could adjust to change how we're preparing our solids going into our filters? Presence and types of iron, manganese, and ammonia oxidizing bacteria. Benefits and challenges being presented by the removal mechanisms being used and the natural nature of your water. And then the options for addressing those challenges and harnessing any benefits that maybe you're not harnessing. So, filter parameters, key ones are filter freeboard, we'll look at that, I guess I'll just read these out. Media loss, core samples, media condition, flock retention, review the media sizes, the bed depths, and adequacy of the backwash. And these center ones, 4 here, can be done before and after backwash, or should be. So freeboard is just as simple as you find if you're in a pressure filter, you can measure from the top of the manway. If you're in a gravity filter, you can measure from the top of the trough, and just measure down to the top of media. And also just look at the filter bed after you backwash and see, is it wavy? Is there any sinkholes in the corner? That's things you can do regularly, just to assess if there might be under drain issues. Or if you've just maybe been backwashing at a rate of something like troughs, you've been losing, flushing anthracite over the tops of your troughs. Core samples, I found you want to make sure you drain down your filter first. Don't let it get dry, but drain it down all the way into the under drain gravel. So that takes some planning, because if you're going to do this, you got to think, okay, we got to drain down our filter, somewhere to get that water to get into the filter, and you got to think about, cleanliness. So disinfect all your equipment. Usually have a bucket there. with some chlorine solution in it. If there's plastic booties you can get, there's rubber booties. Piece of plywood to put down in the filter bed. And then a 2-inch PVC pipe with a screw-on cap, and just bevel the end so it's a little sharp, and then you just kind of push it down in the media bed, and it helps to rotate a little bit. And you put the cap on. I usually bend it like way over to the side and then pull it out because you want to get some suction and have gravity work with you too. Try and pull it out at an angle so you get as much of that as you can. So you can see here, this is probably before backwash, this is after. This is an example where a lot of times you won't get, here's about 16 inches, looks like. So we didn't get a lot of our sand, but we get enough to learn what we need to learn usually. Yeah, I've done better, but I mean, you're not going to get it all the way down to the underdrain gravel. Some of it's going to slide back down. And then when I take it out, you just take the cap off the top and kind of bounce the end and kind of blow, and just kind of, how long it is. So you get, just practice, you get good at it. So we look at the appearance, condition, and depth. Presence of mud balls, you look at interface here, it's a key spot. If you're getting a whole bunch of manganese or concentrated here or iron concentrated here, maybe you size this top layer differently or the bottom layer differently. And you can do laboratory analysis, we can take samples and send them in and say, is there iron bacteria in our filter? What types? Is there manganese oxidizing bacteria? I'm going to look at that just a second. And then the other thing, if I do see spots, we pick at least a couple spots. We grab like a 50-gram sample out of there, and that's used probably at the interface, one down here. And that's used for what's called this flock retention analysis. You take that 50-gram sample, you put it in a 100 milliliter Erlenmeyer flask, which is like a flask shaped, like that with a straight top. And you just rinse it for, I think it's a minute. You dump that together, you do that 5 times. So you get 500 milliliters. Shake that up and measure the turbidity, and then you can plot that versus the depth, media depth, and see where that'll help you too on where you have problems with your filters getting too dirty into mud ball territory, or maybe not getting clean enough during backwash. And these are the guidelines. So you see that here we're getting after backwash we're good, pretty good. We're 30 to 60, we're probably in that range. Before backwash, you see we're getting a lot of concentrated. Above this 300 NTU could be mud ball forming. But I think my thought, I've seen up to 1,000 more. As long as you're clean after backwash consistently from year to year, I wouldn't worry too much about what it is beforehand. But it could help you. It still can help you say that maybe we could size our media different. That's where that would come in handy. But as far as backwashing, as long as you're getting up in that clean filter area, you're good. Filter run length parameters. Just think of the total volume you're putting through your filter versus the total volume of water you're using for your backwash. Looks complicated. That's basically all this is. And then just see the efficient. What percent of the total water that's going out in the system that's not being used for the backwash? So your total water, filter plus your backwash, and then minus. So you subtract out the amount filtered minus your backwash volume. And that's your efficiency. It's called that production efficiency, and that's a good thing you can keep track of too from year to year and see if that's changing. So I don't know, you probably could set up I don't know that I've had anyone do this, I recommend it, but set up so you can actually track some of that on your skate. If you have flow meters for your backwash, you have a flow meter for what's going on in your filter, you could easily keep track of that all the time. See what your production efficiency and where it's going to. Backwash parameters, duration, how long are you backwashing? Are you backwashing too long? Not enough? Turbidity variation, that's what we plot. Some of those plots we saw, the rate, the media expansion, mapping the fluidization, and looking at underdrain conditions. So we'll look at those in more detail. This is a figure we've seen a few times, but that's the basic chart. This is probably more relevant to surface water in terms of the 0.1 NTU. Visual backwash operations. When you start up your backwash, you obviously can look and just see, is it all starting up in one corner, and then eventually towards the end gets over this corner? You'd want the whole bed to rise at once. That's what you'd like to see. And no boiling in one area, just everything just kind of rising, and all solids coming up equally and the cloudiness in the same area. That's just what you want to look for a good, healthy backwash. And then you grab samples. I like to do every minute. So if you have like a 15-minute, 10-minute, whatever backwash, you just, if you're in a, I guess both of these too, whether you're getting in core sample stuff, you of course have to think of all your safety protocol, fall protection. And if we're sitting up here at, with a bucket and you've got a center column filter and you're throwing the bucket down, it takes pretty quick to get in a minute to get the bucket down, fill it up, get it back up, and, you know, your partner, grab a sample, and then you're already doing the next one. It goes pretty quickly. So I usually use a rope, a bucket, tie the bucket off, so if you drop it, you're going to be able to still get it back. And you just keep these now. Of course, the thing is that it's sitting here, you can even see here, it's settling out here in the bottom. So whenever you're measuring your turbidity, you want to make sure you shake that jar up real good. And in general, if you are getting turbidity above the range of your thing, you can dilute and measure turbidities. And it's not bad to keep, after you've done your study, to keep some smaller vials. You have to see if the color changes. You can take pictures too, but then you can say, here's the turbidity, kind of the color that we shoot for. And just show your operators. And then you can see if that, maybe at different times of year that's different. Or just set your time. So there's that profile. American Water Works Association recommends determinate at 15 to 25 NTUs. So you see that's like right kind of in there. And a lot of times people backwash well beyond that. So even if you're reclaiming your water, that's still time if not water that you're wasting, that you could turn your filters around quicker if you just say, you know what, we're here, we're not really getting much return on our investment of added water, we're flushing through the filters. Here's an example of a simul wash where you have your air and water. So your low rate backwash, that really does your cleaning, and then your restratification backwash. The next thing is assessing the expansion of your media. Here's this tool that they use. There's different versions. And this is more for a pressure filter. It's got to be a little smaller. There's a big one used for gravity filters. But you can see in the clear columns, there's just different length tubes. You've got to have good connection hardware. This one especially, since it's in the center column filter, it's real deep, because obviously when this media fluidizes, it becomes quicksand, that thing would just disappear. And I've had to dig those out a few times. It's kind of fun. But, so you get it in place. These boards here are not for this part, but we'll talk about that in a second. That's, you can zip tie boards onto your backwash troughs for the assessment of your if your bed's fluidizing everywhere. You do that with a probe. But you have a connection point up at the top and a connection point down at the bottom. And you're going to set that right at the top of the media. You want to make sure, again, it doesn't sink, because this is what we're using. If these two tubes fill up with media, after you take it out and this one doesn't, we know that we fluidize right between the top of those two tubes. And then we can take that distance and divide by the depth of our bed, and we say that's our percent expansion. That's basically what we're explaining here. Targeted 30% expansion. That's pretty good. I think 25 can still be good. Really, flock retention tells the whole story, because if you're getting your media clean, it's probably good enough. Again, I guess this is more surface water, but warmer water, because it's going to be less dense, you're going to require more velocity, so it will change for surface water plants. And this is that, you can use a probe and like a 1/2 inch copper with the ends plugged is a good tool for that. And just push down while you're backwashing and stepping on those boards and feel, where if you have a support gravel, where that is. And you can also just slide this back and forth. There shouldn't be a lot of resistance, because the media should all be like quicksand, all fluidized. And if that's not happening in certain areas, you can chart that and say, okay, contours of here's where it's fluidizing and here's where it's not. And you can identify, well, here's an area, maybe we want to put a box. You can build a box, maybe this high. One of your younger guys can fit into, and you can tell them to get in there and dig, and you can dig down and push the box down, and then look at the if there's a problem with the support gravel or the underdrains. Thing to think about when you're on when you're down there, I guess, is this whole idea that you have to think about safety a lot there too. I mean, if you don't want to follow the media when it's fluidized, I was thinking about this one night. I saw what happened to the expansion fluid. And I thought, what would happen to me? I better be nice to these guys who are up top, make sure everything's straight between us, you know. Because they go, oh, Nelson disappeared. Shut off the media. Oh, time for lunch. You'd just be encased with like a hand signal. But yeah, so I think, you know, there's things to think about how you're going to handle that. If you could probably have a, you know, just like you would with a rope or something like that, it's probably a good idea with a harness so that if a guy does fall in, a partner can help pull him up. And that rope should go up above, not just, should have at least 2 guys down there too.
Around the waist, not the neck.
Yeah. Like my the Norwegian life jacket, it's just got a suction cup for me with a big floating ball on the top and a flag, so make sure she gets her life insurance. Yeah, so then this is Rick and Brian and I are down here probing, and he's we yell up to him like we're going through a grid and tell him whether it's good, not so good percent fluidization. And you just, you know, prepare a report, or you can prepare and actually do a work session. Just discuss what you think you've learned, what we found, what areas maybe we could make changes on, and document those. It's good to have a database, I think, especially with that production efficiency and maybe the turbidity curve and the head loss curve. And as far as frequency, the chemical evaluations every 2 years, and I actually think a lot of these you probably want to do annually at first, but then after a couple of years, maybe go every 2 years, and maybe up to 5 after that, you know. But I think it's a good idea too, as you're getting ready to do a renovation, to do one of these to say, you know, what can our filter teach us about the depths of our media, other things. Maybe we should make a change when we replace the media next time. So again, here's the definition, how to make sure it's customized, some of the benefits of increased insight, and I've seen even these lead to being able to push out renovation of a plant always, because you actually get more production on your filters. So there can be real paybacks for relatively inexpensive study. So that, I'll wrap it up and open it up to questions.